Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 8.2, day 3, entitled Graphs of Polar Equations. And today we're going to talk more about how you can test for symmetry when you've graphed a polar equation, and again, how you can use your graphing calculator to do even more complicated graphs of polar equations. Now there's basically three types of symmetry that we can have for our polar equations. There's symmetry about the polar axis, which is really the x-axis. And then there's symmetry about the pole, which is the origin. And then there's symmetry around the line pi over 2, which is really your y-axis. And there's ways that we can test for this. Okay. The first way is to check for symmetry around the x-axis. And that's if you replace theta with negative theta. If you get the same thing when you substitute a negative theta in for the theta, then you have axis around the pole, or symmetry around the polar axis. For the origin, which is in number 2 here, you can replace r with negative r, but that's really only when you have an r squared in your equation. The other thing you have to do for this, for the origin test, is to replace theta with theta plus pi. And that's what's being talked about down here in this red note. And you're going to do that when you have an r in your equation. So if you have an r squared, replace the r with the negative r. When there's just an r, then you have to replace the theta with a theta plus pi. Because remember that r theta and negative r theta plus pi gets you to the same location, to the same point. And then to test for symmetry around the y-axis, you want to replace the theta with theta minus pi right here. So it depends on what equation you're dealing with and what origin test you are really doing. But you can do all three of these to any equation. Okay. And here they show some pictures. These are in your book as well. This first graph, the graph on the far left here, and then the graph on the far right are symmetric about the pole and pi over 2. So remember, the pole is the origin, so you can see that this is a circle, so yeah, it better be symmetrical around the origin. And pi over 2, so you could cut it in half. Technically this one, you could argue would be symmetrical around the x-axis as well, since it's a circle. This last one here on the right, that's your rows, so that's going to be symmetrical around pi over 2. I think you could argue that it could be symmetrical around the x-axis as well. And then this one here is also symmetrical, but it's just symmetrical around the pi over 2. Okay, so in your book they do have a couple examples there of the different types of symmetry that you can see. But let's test this out. Let's take a look at this equation here. We have r squared equals 9 sine theta. And we want to test that for symmetry with respect to the polar axis, the pole, and then the line, pi over 2. So that's all three of our tests. Okay. So if we're going to do our polar axis, which again, remember that's really our x-axis, we're going to replace theta with negative theta. Oop, negative theta. So I'll have 9 sine negative theta. And remember, sine is one of those ones where if you take the the sine of an angle or the sine of a negative angle. When you take the sine of a negative angle, that negative kind of pops out front. That's that even-odd property that we've talked about in the past. So you end up getting negative 9 sine theta. So it's a different equation because it went from positive 9 to negative 9. So no, there's no symmetry around the polar axis for this one. And then we do want to check for symmetry around the pole, which is really the origin. So this is where there's two possible substitutions that we could do. Since our equation does have an r squared, we want to substitute negative r in for r. So we're going to put negative r in for the r. So, when you take negative r and you square it, you're going to get r squared back again. So it'll be the exact same thing. The right-hand side of the equation, there's no r to substitute in, so that would stay unchanged. So we would have r squared equals 9 sine theta. So yeah, this is going to be the same equation. So there will be symmetry around the pole, around the origin for this equation when we graphed it. And then the last test is for symmetry around the line, pi over 2, which is really the y-axis, remember. And here, this is where you're going to replace theta with pi minus theta. So this one's going to have a little more work here. We'll have 9 sine pi minus theta. Now this part here, this sine of pi minus theta, that's our subtraction formula. So we'll take 9 times sine of pi times the cosine of theta minus the cosine of pi times the sine of theta. Now when we simplify the sine of pi and the cosine of theta, the sine of pi we can evaluate, and that's going to be 0. And 0 times the cosine of theta, even though we don't know what theta is, 0 times anything is just 0. And then cosine of pi is 1. And sine of theta, I'll just say sine of theta. So 0 plus sine theta is sine theta, so we'll have 9 times the sine of theta, which is the original equation that we had up there. So yes, we do have symmetry about the y-axis. So you can have one kind of symmetry, you can have two, you could have all three. You could even have no symmetry. But your homework tonight is going to have you doing more of this testing for symmetry. So for example 6 here, before we graph it, this is a new type of a graph that we haven't seen. And this is the French word for snail, I think it is. I'm not exactly sure how to pronounce it. But this is another shape that we haven't seen yet. It's kind of like a cardioid, except it has a little loop on the inside of it. Okay. So I guess somebody looked at it and thought that overall shape kind of looked like a little snail or something like that. But before we graph this one, let's do our test for symmetry, because if we know the type of symmetry it's gonna have, that can help us to make sure that we get the graph correct and that we're connecting our points correctly as well, so that it has that specific type of symmetry. Okay, so let's do our test for the polar axis, which remember is really the x-axis. And that's where we're going to replace theta with negative theta. So I will have 1 plus 2 cosine, oops, I don't need the parentheses around the cosine. I need the parentheses around the theta. 2 cosine negative theta. There we go. Now again, cosine is one of those ones where you can take the cosine of theta or cosine of negative theta and you get the same thing. So this actually ends up being 1 plus 2 cosine theta. And again, that's that even-odd property. So we actually get the same thing back out again. So yes, this is going to have symmetry around the polar axis. If we test for symmetry around the pole, which remember is just the origin, we're either going to replace r with negative r if we have an r squared. We don't have an r squared here, okay? So we're going to replace the theta with the theta plus pi. So let me do this because this will show you the other type of substitution. In the previous one, we replaced the r with the negative r, so now we're replacing the theta with the theta plus pi. So we'll have 1 plus 2 cosine theta plus pi. And again, this is going to be an addition formula that we're going to have to write out. So we'll have 2 times cosine theta times cosine pi minus sine theta times the sine of pi. And then we want to take the cosine of pi, which we can evaluate, and the sine of pi, which we can evaluate. Cosine of pi is going to be negative 1. And the cosine of theta we don't know, so we'll just leave it cosine theta. Sine of pi is going to be 0, and 0 times sine of pi is still 0. So then if we distribute the 2, this minus 0 just kind of goes away, but we could distribute this 2, so we actually end up with 1 minus 2 cosine theta, which is not our original equation. We had 1 plus 2 cosine theta. So nope, no symmetry around the pole or around the origin. So that means that our graph isn't going to be centered around the middle. It's maybe going to be shifted off to the left or the right, or maybe even up or down. And then the last one is to check for symmetry around the line, pi over 2, which is really our y-axis. And here we're going to replace theta with pi minus theta. So again, we're going to have another addition or subtraction formula that we're going to have to use here. So we'll have cosine of pi minus theta. So I'm taking this original equation and I'm just replacing the theta with the pi minus theta. So let's see, our subtraction formula then is going to be cosine of pi times cosine of theta plus sine of pi sine of theta. Now again, we can evaluate the cosine of pi and the sine of pi. Okay, cosine of pi is going to be negative 1. So this is going to be negative cosine theta. Sine of pi is 0. So 0 times sine of pi is just 0. And then if I distribute, remember that plus 0 goes away. So I'm really just distributing the 2 to the cosine theta, or negative cosine theta. So again, I get 1 minus 2 cosine theta, which is not what we had originally. We had the plus. So nope, no symmetry around the y-axis either. So there's really only going to be symmetry around our x-axis, which is our polar axis. So if you look at our graph, however it's going to be graphed, if you kind of folded the graph down from top to bottom so that this polar axis, this x-axis, was the crease in your paper, then what's above it and what's below it will be the same. Okay, so that's good to know. Now let's actually graph it. And we're going to basically make a table of values like we've done in the past. So I'll have r and theta. And again, we're picking the values from 0 to 2 pi, but we're only picking every fourth. So we'll have pi over 4, pi over 2, 3 pi over 4, and then we'll have pi. Now remember, once you do 0 to pi, those are really the only values you need to do because the rest are going to be symmetrical with what you've already done. So 5 pi over 4 should be the same as 3 pi over 4. 3 pi over 2 should be the same as pi over 2. I'm going to run out of room, so I'll write the rest over here. We'll have 7 pi over 4, which should be the same as pi over 4, and then 2 pi, which will be the same as 0. Okay, so then I'm going to take all of these radian values, I'm going to plug them into theta. We'll take the cosine of that, we'll multiply it by 2, and then we'll add 1. Okay? So cosine of 0 is going to be 1, and 1 times 2 is 2, plus 1 is 3. Pi over 4, cosine of that is going to be square root 2 over 2. So when I take the square root of 2 over 2 and multiply it by 2, I get the square root of 2 plus 1, make it a decimal, that's about 2.41. So the square root of 2 is 1.41, add 1 to that, you get the 2.41. Pi over 2, the cosine of pi over 2 is going to be 0. 2 times 0 is 0, and then you add the 1, so you get a 1. Okay, we really only have 2 more substitutions to do here. 3 pi over 4. When I substitute that in, that's going to be negative square root 2 over 2. So 2 times negative square root 2 over 2 is going to be negative square root 2, or negative 1.41. So 1 minus 1.41 will be negative 0.41. So again, remember, you can have a negative value for r. That just means you go in the opposite direction when you graph it. And then for pi, okay, pi, cosine of pi is going to be negative 1. So 2 times negative 1 is negative 2, plus 1 is negative 1. So those values right there then are going to start to repeat. So 5 pi over 4, that's going to be the same as 3 pi over 4. 3 pi over 2 will be the same as pi over 2. And then the 7 pi over 4, that's the same as pi over 4. So I'll get the 2.41. And then 2 pi is the same as 0. Okay, so you can see the symmetry in your table of values. We've noticed that in the previous section of notes as well. And you can use that to help you graph. Okay, so as we graph this, remember, plot a few points and then connect them, plot a few more and connect them. So we're going to start at 0 degrees, and we're going to go 3 units out. Then I'm going to go to pi over 4, which is right here. And I want 2.4, so almost to like 2.5. Pi over 2, I want 1. And then 3 pi over 4, which is over here, I have to go in the opposite direction. So instead of going up 0.4, I'm going to go back 0.4. It's kind of hard to see on the graph there, but maybe right about there. So far, I've gone up and over. And then this curve, when you make it, it needs to kind of come down like this. Okay. We're kind of swooping into our fourth quadrant here. My value for pi is going to be back 1. So then I'm going to complete that little swoop and come back up to the axis. Okay. Now, if you used your properties of symmetry, think about how you would make this same pattern repeat below the x-axis. See if you can kind of visualize that and see where we're going to be going as we graph it. Okay, 5 pi over 4 is going to be right here. But I don't want to go on the 5 pi over 4. I'm going to go back the other direction, about a half. 3 pi over 2, I'm going to come down 1. So now I've kind of gone up to that point, and then I've looped around again to this 1. And then at 7 pi over 4, which is over here, I want to come out 1, 2, and a little bit, 2.4. And then at 2, I'll go back up to 3. So, oops, it's not very curvy there, but it loops around like that. Okay, so it's kind of like the little cartoid that we did, except you have this little loop-de-loo on the inside. So maybe it looks like a funky earring or something like that if you kind of turned it on its side. Okay. Now, this is the book solution. They talk about the different types of symmetry. And they say that, yeah, there's symmetry around the x-axis like we found. You can see that in the picture here. Here's our x-axis. It's the graph's the same on the top as it is on the bottom. Granted, mine's a little sloppy because I'm doing it by hand. Okay. And then again, the book wants you to think of it like your cosine curve when you're making your table of values. Don't actually draw out that cosine curve. Don't do that. Just make the table of values like I did. And then there's a nicer, prettier picture of what it's supposed to look like. So there you can really see the symmetry right through the middle here. Okay? So that red part and then that blue part. Okay, if you kind of folded the graph in half, folded it down on top of itself, everything would match up. Okay, so it was good to know that I had that type of symmetry before we actually went through and graphed it. That's helpful. And again, these types of curves, see, they are named after the French word for snail. So somebody looked at it and thought it looked kind of like a snail. That's how it got its name. And they are always going to follow this format where you have a number plus or minus a number times cosine theta. So we had 1 plus 2 cosine theta. So you're not necessarily going to have plus minus. It just means you could have 1 plus 2 cosine theta, or you could have 1 minus 2 cosine theta. And same for the sines as well. So anything that follows this format is going to be one of these snail type of graphs. And again, we had that table in your book on page 552 that had all the different types of graphs. So this is in there. They have different pictures of the snail graphs and they have these equations. So you can go back and review that if you'd like to. Now, when you're graphing on your calculator can handle very basic stuff and then it can also handle really complicated stuff like this one. Okay? Now, this equation here, we have r equals sine theta plus sine squared 5 theta divided by 2. Oh, sine cubed 5 theta divided by 2. Now, if you're going to type this into your graphing calculator, you're going to go to the y equals, which make sure you're in polar format. So make sure you've gone to your mode, make sure you've changed it to polar. Okay? And then that'll automatically change them from y equals to r equals here. And then when you type in sine of theta, you have to hit the X button and the calculator will automatically put in the theta for you. All right, now here's how you type in the sine cubed. You have to do parentheses, and then you have to do sine. Your calculator is automatically going to pop up the parentheses for you. And we wanted 5 theta divided by 2. So close those parentheses around the angle measurement, and then close them around the sine and the angle measurement, and then do to the third power. So you can do math and then 3. It'll automatically cube it for you. Okay. And then when you graph, if you do zoom 5, that'll do the standard graph. I don't know why mine is off on the screen. Let's try zoom 0 maybe to make it fit. Okay, there we go. That's a little bit better. So there you can see that crazy, funky, looks like some crazy flower or a head of cabbage type of a graph. I don't know if this one has a fancy name or not. But when you do zoom 0, that makes it automatically fit on the screen. But let's go back for just a moment and talk about what the range would actually be for this one. Okay. Since we're dividing by 2, normally sine has a range of 2 pi. Goes from 0 to 2 pi. So since we're dividing by 2 here, we actually have to multiply the range by 2 to get our full range for the graph, which would be 4 pi. So you could change your window settings if you wanted to. And since pi is about 3.14, if we multiplied that by 4, here they've got it set to 15.7, okay? So that might be close to that 4 pi value. Okay, so let's do another example, one that's not quite as crazy, but one that's still better to do on your calculator than by hand. And we've got r equals cosine of 2 theta divided by 3. Now again, remember, normally cosine has a range of 2 pi. And since we're dividing by 3, we want to multiply by 3. So we really need our settings to go up to 6 pi. So we want to set that in our window. So let's go to our graphing calculator. I'll clear out the other one. And let's do cosine of 2 theta. Come on, theta. There we go. Divided by 3. Then close your parentheses. And then if you do, let me just hit graph and see what pops up. Okay, it doesn't fit on the whole screen. So let's do zoom 0 again so that it will automatically fit on the screen for us. Oh, I didn't connect to that last little piece. There should be another little piece in here that gets connected. I don't know why it's not doing that. Let's take a look at our settings here on our window. We wanted to make sure it went all the way up to 6 pi. So let's do 6 times pi here. What should that decimal be? 18.8. So let's change this to 18.8. And then let's do that for the y too. Well, y, no, y we don't have to. It's just for our domain that we have to do that. Okay, so now let's go to graph. See if it connects that last little piece for us. There we go. Okay, so now we have this last little piece of the petal that got connected. Once we made our domain bigger, or our range bigger, we changed our settings, made that bigger, then we were able to see the whole graph. Okay, so on your homework, there's going to be some problems where they want you to do that, where they want you to graph these, and you want to put them in your graphing calculator. There's a nice pretty book picture, okay? So these, you don't have to make a table of values for to graph. If they want you to do that, just, draw a rough sketch of what it looks like. Okay, but remember this, this calculation that you might have to do. If you're dividing by something, take 2 pi times that and then put that in for your x values in your calculator. Or what was that actually called in the calculator? That was your theta values, your theta max. Okay? So this should be your theta max in the calculator. Okay, that's what that value is going to be. And that'll make sure that you can see the whole graph when it's actually graphed. And remember that you can also do zoom 0 to make the graph fit the whole screen. So take a look at these practice problems. There are some evens that you're doing. I want to say that those aren't in the back of your book. I think the back of the book just has the odds. So make sure you check the binder in the classroom where the solutions are worked out, or take a look at them on the class website. They're worked out in a PDF there that you can see as well. And definitely if you have questions, come on in and see me before school, because some of these graphs, these snail graphs, these are the most complicated ones we've seen so far. But if you've done the previous sections of homework with the graphing, you should be fairly confident in your graphing capabilities. Some of the stuff with the testing for symmetry can get a little crazy too. So if you have questions, come on by and see me.